I will introduce our work for social boot detection, and I will leave some time for listeners to ask some questions. So let's get started. And yeah, our paper is for the social boot detection and is for the boot detection on social platform like Twitter, Facebook, and so on. And we proposed a very novel approach by extracting significant behavior patterns from raw user logs. And our evaluation work proved that these effective behavior patterns can achieve a very high accuracy and record and performance. So I will introduce one by one and step by step. So firstly, our motivation is that, the boot accounts are floating popular social network. Leads to some very harmful problems like fake news, spam, rumors, and misinformation. Also, our users, the normal users in the platform, may lose their money, their mental and body health, and lose their trust in the platform and the applications. So the social boot problems lead to very high maintenance and risk control cost for the companies. It means the employees need to deploy very large models to detect social boot using their very large amount of storage and computation resources. And also, if some boots are not prevented and avoided, it showing on the platform, the companies also lose their reputation. So our goal is very clear. We want to design a very high accurate and very easily deployed detection system. So there's our challenges. So firstly, based on reading a lot of related works, we find a misaligned clock problem in many modeling work. It can lead to noise and information loss. It means the engineers often modeling a account based on the account-based account features, but they didn't realize those accounts are in their different life cycle, which means the time from the registration to the detection time are different. So this is the first challenge for our work. And the second problem is the scale of industrial data is very immense. It's very large. So as we talked before, it has to restore more data and modeling more data. If we use a very large model, we just input all the raw features, raw data to an algorithm is not practical. So these are two main challenges for our work. And our contribution is that, firstly, we not do a black box work. We do a very detailed measurement based on the behavior features and extracting the patterns in our work. We want to find the difference between the normal users and the social boots to observe their the different distributions on our data, and that will support the following system design path. And our main contribution is that we built and designed a system called BotShape. BotShape, it means it has several advantages. Firstly, it defined the life cycle concepts to solve the misaligned clock problem. And then it compressed very large of data, industrial data, to lightweighted features, behavior features. And thirdly, we mine the significant and useful pattern features and also evaluate them on a real world data set. And the result shows that the accuracy, average accuracy across different classifiers is very high, both on the accuracy and F1 score. And we will show the detailed result in the following. And firstly, we want to introduce our data set. The data set is a very popular one. It's called CRISIC. Yeah, it's collected from the real world on the Twitter platform. It has more than 10,000 real accounts and 10 million tweeting logs. Tweeting logs means if the account posts a tweet, the system will has the tweeting log. Yes, and we can see the scale of the data and the period of the data, also very high quality. It has a lot of instance, and also the period is very long. And we will, however, I want to emphasize at this point, yes, the raw data is very large because you can see the raw tweeting logs is very large. And then firstly, we want to do some measurement on those, just like I said, we firstly do some measurement work to find the difference of distributions on some behavior features between the normal users and the social groups. So these the picture. The two pictures are monthly, a monthly count of tweets of social groups and the normal users. The left one is for the boot count, and the right one is for the normal users. Yeah, and we can say, sorry, I made a mistake. In each sub picture, the left one is the normal users and the right one is the boot account. And we can say that the count of tweets are evenly distributed across 12 months after the account's registration. But on the right, the boot accounts, we can see these suddenly become inactive after the 6 months. So according to the according to the two pictures, we find the difference are so obvious, so clear. And the left sub picture is accumulated of the counts. So we can find the conclusions as the same. Yes. For example, on the right picture, we can see the accumulated accounts will not increase after the 6 months. And we also we change our time interval. They change it to the weekly, yeah, not monthly. We want to find some fine-grained trends and the distributions patterns. And we can also find the similar conclusion. Yes, the normal users, and after the first 21 weeks after its registration, we find it's always active. It means that it sends tweets day by day, but we can see the boot account. And firstly, it has no active activity. And then the burst from the 7th to the 9th weeks, they sends so many tweets, but then their activity become very low. Yes. So I think it's very important for us to conclude that from the behavior perspective, normal users and the boot accounts are different totally. And then from we also want to mine some different patterns from the raw time series to find more useful features for our classifier to predict. So we do this work. Firstly, we analyze the seasonality of the time series. So the seasonality is often used to analyze the busy and idle time for time series. If the account is controlled by a normal user, treating activities well affected by his work and raised behaviors habits. Means, for example, when people is at work, he will not send Twitters. Yes, maybe before going to bed, he sends some tweets. So we can see the trends across the day are different. Across 24 hours in a day are different. And the left picture shows the hourly seasonality, and the right pictures showing the daily seasonality. We can find the trends, a local opposite. Yes, we can find from 0 a.m. to 9 a.m. the trends, the trends for normal and the boats are totally opposite. And also we can see in the daily seasonality, the highest point for the boots is at Saturday, but it's the lowest point for normal users. So we can see the seasonality distribution are totally different. And we also use the seasonality as our features for further prediction. And also, we also want to find some gathering information of boots based on our assumption that the boots, their behavior patterns are very similar. So we cluster our accounts based on their behavior sequence. So the method is that we firstly using a time series shaping features pattern mining algorithm to build some middle features, and using k-means. It's a clustering algorithm, and then we grouped our accounts into 8 different clusters. We plot the clusters using their raw behavior sequence based on its cluster ID in separately for the normal users and the social boots. So we find, it's very different. So you can see the shape of the normal users on the left picture. They are totally different, very various, which probably because the users has different user habits. And the left picture is the social boots. We find, it's very similar. Yes, the shape of wave of their behavior sequence is very similar, which can support our assumption that we can gather in boats based on their behavior. So we also use these the middle features, the shaping features, as our features in our system for prediction. And in the evaluation part, we will prove that it will significantly improve our accuracy. It's very useful. So fine, based on the measurement, we talk a lot about the distribution between social goods and normal users. Now we proposed our system combined the aspects we talked before, and it produced a very high accuracy. So the input data is the tweets and the behavior logs of the users, and also the users' registration informations, like its registration time steps. And then the main part is the feature engineering part. Firstly, it constructs the behavior sequence, and then we use some algorithm to extract its seasonality and shipping features from the raw behavior sequence. And then we use those behavior features for our classifier to predict boots. So the output is the label. Means it's a positive or negative, is both normal users. And I just remember that we proposed six concepts, means the misalient clock problem, which means we should design method to solve this problem. We need to elaborate the accounts, the features, their standards. So firstly, in our system, we define the life cycle concept. We use based on the time step of the user registration and the tweeting time step, the 2 time step volume. And so besides the first effect, also the concept of life cycle also for the system, it becomes easier to aggregate behavior statistics. For example, we can use the time window and to calculate the count of tweets located in the time window. Yeah. And we can also setting various time intervals like weekly, hourly, daily to calculate different statistics in this window. And then the first feature engineering part is behavior sequence. So just like I told, the time intervals can be various, daily, weekly, monthly. Like the measurement part, we can conclude from the different time interval, we can observe different distributions. A more fine-grained time interval provide more information for the classifier to predict. So, and also we to collaborate the state of the accounts. So we set the life cycle as 1 year, means we extract features and modeling them from only the tweeting logs in 1 year from the registration time to the modeling time. So the result, we can construct different behavior sequence with various dimensions based on the various time intervals. So that's the result. We can see in detailed dimensions. And the next feature engineering part is behavior patterns. yes, as we talked before, the seasonalities and the shipping of the time series is very useful for, to distinguish boots accounts from normal users. So here we also implement and design the two parts in our system. Yeah, the first seasonality, it means the regular patterns existing in a time series. So we using the averaging. We just simply average according to its time to calculate the seasonality. So we define two types of seasonalities, hourly and daily. Yes. And the second part is the shiftlets features. It means the subsequence or pattern from the time series, but it can distinguish, but it's very informative and distinctive for some time series classification problems or prediction problems. It's a very general time series features extracting method. And so we set different compression ratio. The compression ratio means the row, means from the length of row sequence to the shiftless sequence. So the weekly setting is 30%, and the monthly, because it's not very long, it's only 12 dimensions. So we set the compression ratio is 50. And okay, so then according to our system design, we will input all the features, including behavior sequence and behavior patterns, to the upstream classifiers. So we design our evaluation part. We want to answer these questions. Yes, how efficient our features, behavior features, and whether it's broadly effective for our features. So we design 4 problems. Yes, and then in our evaluation part, we will use the result to support that we achieved it, our system achieved it. The first one is BotShape can have high performance across different boot ground truths and different classifiers, and also compared to some traditional features like count profile features, we also improve. And then we can see prove a problem that we use less data by extracting pattern features from the row sequence features, but we also get higher accuracy and performance. So the result, yes. The first, I simply and quickly introduce this. According to the real-world dataset, because the boots, the category of boots are different, so we grouped them into 3 ground truths. The first one is the most simple, only contains the social boots. The last one, it has social boots, traditional boots, and fake follows. Fake follows also is a boot count, kind of boot count. So we have 3 ground truths, and we will evaluate our performance on these 3 ground truths separately. And then this picture in our papers, yes. So the first problem is, the first we want to prove is that our behavior features can improve across different classifiers. So you can see the, yes, we use 4 popular classifiers, the SVM, and so on. So, and we see the pattern, this line pattern is the final accuracy So we can find that the accuracy is very high and the average is 98.552. And the F1 score is very high also. And the second we want to prove is that yes, we can. Yes, we can. The second one is we can compare to traditional features. We also gain a lot. So the first column, account, is meant account-based features, and not using the not these behavior features. So we can say the original performance has a significant gain after using our BotShape. And we can say on the three ground truths, they all get a very high gain, performance gain on accuracy and F1 score. And the third, we want to prove that on different types of foods, we also have very high performance. So the result has also proved that. So I think it's a very comprehensive comparison. And also, just we talk the fourth one. We want to prove that based on the pattern mining from the original behavior sequence, we reduce the dimension of the features. Means we use less data, but we also have better performance. So the results can prove this point. The gain is the accuracy of pattern miner sequence. So we can also see the gain is very large. Okay, and I give some detailed data to prove that. So we use weekly sequence data features and monthly sequence features. So the compress ratio is 30% and 50%, and the comprehensive compress ratio is 34. So means we reduced our scale of features to 34, but we got a very higher performance. And conclusion part, yes. Firstly, I think our contributions two parts. The firstly is we characterizing our behavior sequence and patterns features. So we shows why they can separate social bots from normal users. Is from a statistical perspective. It let our work more expandable. It's not a black box. And then it support our following system design. And also the design of BotShape is very great. Firstly, it solved the information compressing problems in industrial environment. It shows it compressed the tons of raw tweeting logs to very efficient features with very small dimension of features, and it will naturally reduce the cost of restoring and restore and computation. And also we propose the very novel behavior features work, and we also address the effects of behavior features for bot detection. Yes, it's very useful. We prove that using our result. And we also designed the pattern mining modular to extract very significant patterns from raw time series of behavior sequence. So, and we find it largely improved the accuracy and F1 score for bot detection. And so in conclusion, the design of BotShape is very reasonable, and the result the evaluation part supports that it outperforms many works. So it also provides a new view for the academic world, that they can use the behavior features to predict boot detection, and they will realize the importance of behavior features of social boot detection. So I think that's the meaning of our work. And thank you for listening. If you have any questions, you can directly ask me, and I will give you also. You can also send me emails.